I'd like you all, just for a second, to imagine a world where plastic was never invented. What would that world look like? What would the inside of your house look like? What would you be doing in that world? Well, you wouldn't be sitting on those plastic seats for a start, but you wouldn't have had your mobile phones with you tonight. You wouldn't be planning your jet-set holiday abroad on a plane. But we also wouldn't be having sterile, disposable medical supplies. We wouldn't be able to produce the food that's required for our ever-increasing population. We wouldn't be able to send people to space. We wouldn't be able to send satellites to space. And we know what that means. It means no GPS. And don't panic, it also means no satellite TV. But what it also means is no plastic waste. And we're surrounded by plastic. And there's a reason for that. Plastic was made to make our lives better, more efficient, more cost-effective, to advance science. And if you can believe it, also to be environmentally friendly. Because most people think the first ever plastic was Bakelite, which was created in 1907. That was the first fully synthetic plastic, actually. So it means the ingredients didn't come from anywhere in nature. The first commercially viable plastic, actually, was created by somebody called John Hyatt. And he set about for a challenge to try and improve an environmental problem at the time, which is the use of ivory for billiard balls, like billiards the game. So he looked to nature, he looked to the cotton plant, and he took the fibres from inside this plant here, and he added something called camphor to it, to the cellulose that's in those fibres. And he created something called celluloid, the first plastic that could be shaped now, that could mimic natural ingredients, natural features like tortoiseshell, horn, and ivory. Now, that kind of ingenuity that he actually had has seen so many further advancements in plastics over that time. And at the time, you can't imagine him, understandably, he couldn't have foreseen our dependence now on plastic, our desire for single use, and he couldn't have foreseen this being an environmental problem. Now, before I talk about that problem, I do want us to celebrate a little bit the characteristics that make us love plastic. It's durable, it's strong, it's hygienic, it's lightweight, it's heat resistant. Those last two properties are the reasons why we put it on rocket ships and it goes to space. We can shape it into whatever we like. And when I say we can do that now with our 3D printers at home. The strength of plastic makes it great for safety equipment like helmets and shields. And plastic fibres, call them synthetic fibres, they're also really strong, which makes them great for safety ropes. Some fibres, like Kevlar, can be twice the tensile strength as steel fibres, which means they can be made into protective outfits, and in this case, bulletproof vests. Now let's talk a little bit more about synthetic fibres, because that as an industry is absolutely huge. The first big commercial success was with nylon back in the 1930s. And it was so commercially successful that they caused something called the nylon riots for these things here. Now, the scientist who was there creating this noticed that you could pull fibres from molten polymer, and when you stretched them and let them cool, they became strong, elastic, and flexible, and versatile. And that's really what kicked off this massive synthetic fibre industry now. And just so you know, back in 2022, it was estimated that the value of that was $66.11 billion US. And I can understand that, because as a population, we desire different coloured clothes, different textures, different drapes. I want to follow a certain fashion. And that means we create so many different synthetic fabrics. But of course, off the back of that, it also means we create microfiber pollution. I'm hoping we're now thinking, do you know what? Plastic's actually pretty great. And you would be right. But like any material, unless we have a plan for its sustainable end of life, then we're going to end up with an environmental problem, where this enters our natural environment and it collects in the middle of our ocean in massive islands of trash. This here is the Great Pacific Garbage Patch. And that transports plastic around the world, depositing off in really remote locations. And then it ends up in the deep sea as a deep sea sink. But along the way, it transforms, it starts to break down. It's getting slightly and slowly away from that original recognizable object, getting into fragments. And these fragments are what we call microplastics. And we define that with a size that they're less than 5 millimeters, because the size is important here. Because at this size, now they become more available to different organisms. They can now be inhaled and ingested. And of course, this causes negative impact. We know a lot more now about the negative impact of plastics. From large plastic items, we know it causes suffocation, it causes starvation, it causes entanglement. And from the microplastics, we know we've got a broad negative effects. It negatively affects reproduction, feeding rates, mortality rates. And it's not even just the particles themselves that cause that problem, it's what we put in them, like dyes and pigments and other additives. And these can leach out into our environment, causing further negative effects. And that's what you're seeing here. You're seeing a dye leach out from that fibre. And what's interesting is this is not even a microplastic fibre, this is a cotton fibre, which then begs the question, is our anthropogenic natural fibres potentially hazardous as well? Now, they don't stop there. They get smaller and smaller. They go from microplastic down to nanoscale. And nano is an incredibly difficult measurement to imagine because you can't see it. So to put it in a bit of context, let's imagine that around approximately a grain of sand measures 1 millimetre. Nanoplastics, so in this case nanoscale, we're going into that, we'd say approximately diameter of a virus is around 100 nanometers. Going smaller still, the thickness of a human DNA strand is around 2 nanometers. And these microplastics will break down to that level. And this is a problem because at that size, they can now pass biological membranes, like the blood-brain barrier. And potentially that means they're even more hazardous than microplastics. Well, lots of people ask me, okay then, so how many microplastics and nanoplastics are in our environment? How many are in the ocean? And that's an incredibly difficult question to answer, as you can imagine. How do you count the uncountable? But it is important that we do so to understand the extent of this pollution, and people have tried. So there is an organisation called 5Gyres that took lots of different studies and those samples and modelled that data to give an estimate. And they estimated that there's 170 trillion plastic particles in our ocean. That's a lot. But it's hard to conceive how big that is. So just as sort of a little reference, Yale University did the same thing, but trying to estimate the number of trees on our planet. And they came out with a figure, 3.04 trillion. Now let's just compare those for a moment. That means there are 56 times more microplastics in our ocean than trees on our planet. And there's good science and evidence to say that that is an underestimate. Because the data that was used, the vast majority of that enabled that estimate, used methods that only captured particles 320 micrometers or bigger. Now I'm going to have to go back to the scale just to put that in context now, because micrometers fall between nanometers and millimeters. And just to give you, again, something to refer to, we say the average thickness of a human hair is around 60 micrometers. So they're not capturing anything below 320 micrometers in those different studies. So they're not being counted. And the reason why is because of those methods that are being used. We use filters, we use pores in filter papers, and if those pores are big, the small bits go through. That makes sense, doesn't it? The studies we do here at Staffordshire University, we do attempt to go as small as possible. We try to go down to 6 micrometers in these particulates. That's about 1/10 of a human hair, isn't it? And we find when we go down to that range, there are huge amounts of microplastics. In fact, the majority are 100 micrometers or less. And interestingly, most of those are textile fibres. Now, when we look at that estimate, 170 trillion, What we have not considered there is the other environments, our freshwaters, our air and our soil. And a lot of people are actually surprised when I say our soils are full of microplastics. They are. We investigated this a little bit further and we took samples from different farmlands in the fields. And we found on average there was 9.2 microplastics per kilogram of soil, like a bag of sugar. Think about scaling that up to a whole field. And now we know that they're absolutely full of them. And they're coming from various places. They're coming from the greenhouse covers, we call them mulching films, the things covering and protecting our crops so we can increase those yields. But they're also coming in from our wastewater treatment plants because we spread sewage sludge onto these lands. And what is that full of? It's full of textile fibres from us washing our clothes, of course. Now, these microfibers and microplastics, they can travel a very long way. And this is how they get into our really remote regions, including our polar regions. We did a study with the University of Oxford, and we were looking at air samples, sediment samples, and water samples for microplastics in the Weddell Sea in Antarctica. And we found out of those samples, there were 82 microplastics. Now, that doesn't sound very much, does it, actually? Go 82. But this is a remote, pristine location. We shouldn't have any microplastics there at all. And interestingly, 80 of those microplastics were fibres. So that then begs the question, well, why? And then how did they actually get there? And that's the thing about fibres. They're small, they're light, and they can travel by air really easily. And we concluded in this study that actually probably the source of these microfibers in the Antarctica were from the southernmost point of South America. Now, of course, what does that mean on a global scale? On a global scale, it means that the activities that we do here and locally can cause microplastic pollution on the other side of the planet. So what do we do about this? How do we take that ingenuity that created this fantastic material and create sustainable solutions for the future? What do? We need to really think about these different areas of ingenuity. We need to think about our plastic use, our plastic culture, sustainable alternatives, or even better understanding how many microplastics there are and where they're coming from. So we need to build something of a solutions-driven ingenuity. And I propose the way to do that is using a multidisciplinary approach. Because we can't expect just one knowledge base or one sector to have all the answers. Not at all. In fact, what we need to do is combine our knowledge and skills and methods together and create creative, ingenious solutions to this problem. And this is really exciting because this is happening right now. I'm going to give you just a few examples. So now there are mycologists, experts in mushrooms, who are looking at how you can make sustainable packaging that's compostable out of those mushrooms. There are artists who use different types of media. They're either plastic-free or they use plastic waste to communicate about plastic pollution. And there are clothing manufacturers who are looking at the best way to create fabric so they don't shed those fibres when we're wearing them and when we're washing them and when we're drying them. And it's this last point that allows me, fortunately, to stand here and talk about microplastics because I'm a forensic scientist and I specialise in trace evidence, specifically fibres from textiles and how they can solve crimes. And forensic scientists have got a real deep understanding about transfer of particulates, transfer of fibres from our clothes into those environments, to be able to answer questions like who did that, how did they do it, and when did they do it. We even have a phrase for it called every contact leaves a trace. And I say that actually that phrase is also relevant for microplastic pollution as well. We've been doing forensic science and forensic fibre analysis for so long, and also using methods that need to be robust, that we have got some advantages here. And in fact, our methods have to be so robust, they've got to be fit for court. Because in court, if we have any errors, this is going to affect lives. And again, I would argue that we need the same robustness in our methods when we're analysing microplastics so that we've got better informed decisions. We've also been going longer enough to be able to develop new methods, more effective methods for detecting and analysing these microparticles, even in really difficult samples. So look, just like this is a sediment sample, and I promise you there are microplastics in that sample. Now, if we share our knowledge and our skills and our methods from forensic science to those who are analysing these microplastic particles, we're going to get more robust data and hopefully better informed solutions. But what can we all do right now to try and tackle this problem? Well, we can educate and inspire each other and the next generation. We need to have conversations about plastic pollution, accepting that everybody has a place and something to give in this, whether you're a scientist, an engineer, a company owner, a consumer, a forensic scientist. If we keep those conversations, we can cascade those down and hopefully make positive change. And whether that change is a different decision in the supermarket to choose a more sustainable packaging type, or whether it leads to a solution that completely eliminates plastic waste. But what we do need to do is start those conversations together and now. Thank you very much.